We're back today. Today we're looking at problem 19 from the review sheet. This is just I took this from the 2018 AP Calculus AB free response. So last year's seniors had to deal with this problem on the exam. So today we're just going to take a look at how we solved this one. Just reading through the problem here. I'm just going to read through it once. It says people enter a line for an escalator at a rate modeled by the function r given by this thing. But I want you to understand that is not an integral symbol there. That is showing that this is a piecewise function. So the rate that people enter when we're between 0 and 3, when time is between 0 and 300, we follow that weird function. Anytime after 300, the rate that people enter the line is 0. So that means people stopped entering the line after time 300. RT is measured in people per second, and T is measured in seconds. As people get on the escalator, they exit the line at a constant rate of 0.7 person per second. There are 20 people in line at time t equals 0. The first thing I want to do is annotate this problem. Okay, we'll see a problem like this tomorrow on the test. So we want to make sure that we can answer this correctly here. So here's what we have. This r of t function is our rate in. It's the rate that people enter the line. So we're going to call that our rate in. I'm going to put that in my calculator. I'm going to make a note that I'm going to put that in my calculator as y1. I don't need to enter the second part of this piecewise function because the function is just 0. Okay, so I'm going to go ahead and go to my calculator right away. If again, when you do this, just make sure you do it once, but you do it accurately. Okay, so going to my y equals here, I want to clear out the garbage that's in there. And I'll just carefully type this in. So here's what I have. 44, parenthesis, t over 100. Obviously, we're going to use x instead of t. And that is to the third power. And we also have times 1 minus another fraction, x over 300. Again, the function says t, but we use x. And then that whole thing is to the 7th power. So again, this is some kind of bizarre function, okay? But I'm just going to go ahead and graph this thing and kind of see what it ends up looking like. For my window, I know this is between 0 and 300. So on my window, I'm going to go between 0 and 300 on my x. I don't really know what to do for my y min and max. When I'm unsure, I usually use -10 and 10 to start. So I go ahead and graph this thing. And what I noticed is, first off, if you don't see anything, that it probably has to do with your y min and max aren't big enough. Here I can see the graph the whole time, but I have too much white space here. Looking at this thing, it doesn't look like it goes negative, or if it does, it only goes a little bit negative. So I'm just going to adjust my window here. My y min I'm going to call -1. My y max I'm going to call 5. Just so I can get a good picture of what's going on here. Okay, so there I have it. That's my rate in. It's stored in my calculator as y1. Now if I ever need that function again, I can either use the graph or use alpha trace y1. Okay, so that's my rate in. My rate out here says as people get on the escalator, they exit the line at a constant rate of 0.7 person per second. So this right here is my rate out. And it's just a constant rate, okay? But I'm still going to enter that in Y2. So I'm going to go ahead and put that 0.7 in for Y2. So going back to my calculator here, I'm going to graph to see what it looks like. Okay, so there's my rate out. What I notice is right when we start, the rate out is bigger than the rate in. Then at that intersection, my rate in becomes bigger than my rate out. After that second intersection, rate out again is bigger than rate in. So right away by looking at this, I can kind of anticipate some things coming. Right at the beginning, the number of people in the line has to be decreasing, because rate in minus rate out would be negative. In between the two intersections, the line is backing up, right? The number of people in line is increasing, because rate in minus rate out is positive. And then after the second intersection, once again, the number of people in the line will be decreasing. So there's like a rush hour here, kind of in the middle there, where a whole bunch of people are entering the line, so the line is getting backed up. After rush hour, right, the line is decreasing with the number of people. Okay. These intersections here are going to be very important, but not right now. The last thing I need to annotate is this last sentence is very important. It says there are 20 people in line at time t equals 0. This is called my initial condition. Now you may say, Mr. Hartz, that wastes so much time labeling this stuff. I promise you that it will only save you time. Going through this and labeling rate in, rate out very carefully, labeling the initial condition, allows you so you don't have to reread the whole problem every time you need to find out a piece of information. Okay? I really highly encourage you to do this, not only on the test tomorrow, but on the AP exam itself. Okay, A says, how many people enter the line for the escalator during the time interval between 0 and 300? So I just want to know how many people got in line. Now, does that have anything to do with the initial condition? No, there were 20 people there, but that means nothing in terms of how many people got into line. They were already there. It also has nothing to do with how many people exited the line. This solely relies on the rate in. Okay? So what I need to do to the rate in is I need to integrate the rate in on the time interval given. So, it's going to be a little long. So to set this up, I'm going to integrate. I'm going to do the integral from 0 to 300 of my function r of t dt. Because that's my rate in. That will tell me, that integral tells me how many people got into line through that whole time period from 0 seconds to 300 seconds. Note, please do not write out 44 parenthesis t over 100, right? That's the same as r of t. Save yourself some time and just write the integral from 0 to 300 of r of t dt. Okay? This answer will tell us the total number of people who got in line. So, r of t, I know from right here, is in my calculator as y1. So to make this life easy for us, I go back to my graph screen, and I'm going to hit Math 9, integral 0 to 300 of my rate in. And it comes out as 270. Okay? So that means 270 people entered the line in the interval 0 to 300. Okay. So that question did not, the initial condition was not important to solving that. I just want to know how many people got in line. If I want to know how many people got out of line, I would have to do the integral from 0 to 300 of 0.7. That would tell me the number of people who got out of line. Okay? But look at B. B says, during the time interval 0 to 300, there are always people in line for the escalator. How many people are in line at time t equals 300? So this, they're asking about the amount of people. Not how many were added, not how many were taken away, not the initial condition, but all three of those things. Right? If we want to know how many, right, just like in the water in the tank, right? We had to know how much we started with, how much we added, and how much we lost. We have to consider all three of those things to solve part B. So what I want to do is come up with an equation that I'm going to use throughout this problem. Okay? The equation I'm just going to call capital A of t. Okay? This is amount of people in line. At any given time. So at any given time, I can find the amount of people in line by taking, I need to consider three things, right? So when we want these amounts at certain times, we have to consider three things. First is the initial condition. So first off, I started with 20 people. Then I have to think about how much I added. Well, to add, I do the integral of the rate. Then I have to subtract away the integral of the people who exited the line. That's my rate out. Now, they never named it, so we'll just say 0.7 C. So it's always initial condition plus integral of rate in minus integral of rate out. This equation will serve us well throughout this whole problem, especially in part D. Okay. So I want to know the amount of people in the line, specifically at t equals 300. So I'll say A of 300. By the way, you don't necessarily have to write this equation right now. You can go straight to what I'm writing now, which is A of 300 equals 20 plus integral 0 to 300 r of t dt minus integral 0 to 300 of 0.7 dt. Okay. That will tell us the amount of people, because it accounts for the 20 people who are there, the 270 people who get added to the line, and the however many people end up leaving the line. That will tell us exactly how many people are there at the end. Now remember, r of t is in my calculator as y1, 0.7 is in as y2, so I'll just go to my calculator, and I'll do 20 plus, math 9, integral 0 to 300 of my y1 function. Again, it's alpha trace minus math 9, integral 0 to 300 alpha trace y2. Okay, and that tells us that there are 80 people in line at t equals 300. Okay, and that's my answer. All right. Now, as I was talking to you guys in class today, I talked about parts A, B, C, and D of this problem. I feel that A, B, and D are very standard questions. C is kind of an oddball. And when you come to the oddball, the one that you're maybe not as used to, like, how do I answer this question? Okay? On the test, remember, you don't have to do it in order. You can skip that one and go do the one you're more comfortable with. Even though part D is challenging, you'll probably be more comfortable with answering question D. What I don't want you to do is sit and stare at C for a long time. Remember, this is a time test. So you don't want to sit there and stare at C and then you run out of time and you didn't answer anything for part D when you could have gotten it right. But we'll do it in order here. I'll take a look at part C. It says, for T is greater than 300, what is the first time there are no people in line for the escalator? Okay. So now we're talking about T greater than 300. The first thing I ask myself is, well, are people still getting in line? Well, when we look up here at our R of T, this piecewise function, our rate of people entering the line is 0 for T greater than 300. Okay? The next thing I want to think about is how many people are in the line currently. Well, I literally just answered that in part B. So there's 80 people sitting in line, and I want to think about how long will it take those 80 people to leave so that there's no more line. Well, all I need to think about here is the rate out. People are exiting the line at a constant rate of 0.7 person per second. Okay? So every second, 0.7 people leave. So when I think about that, that's a number, right? It's going to take me longer. If it was 1 person per second, it would take me 80 seconds. If it was 2 people per second, it would take me 40 seconds for them to all leave. What am I doing with 80 and my rate? Well, I'm just taking the number of people in line divided by the rate out. So I'm going to do that, and I have to remember that however many seconds that takes, that's the amount of seconds past T equals 300. So what I'm going to say is, for part C, yeah, this is the oddball. I don't want you wasting your time too much on this. But I know that the T will be 300 plus however long it's going to take those 80 people to get out. I'm going to take the 80 people and divide by people per second to give me a unit in terms of seconds, right? You can do unit analysis here. This is in people. This is in people per second. When I divide by a fraction, I multiply by the reciprocal, and I get seconds as my unit. Okay, so I'm going to go ahead and do that on my calculator. So I'll do 300 plus 80 divided by 0.7. And I'm going to get 414.286 seconds. All right, T equals 414.286. And that's seconds, and that's the time when no one is in the line. Part D is more important here. It's worth a lot more points on the test. So let's take a look at part D. D says, for 0 to 300, at what time T is the number of people in the line a minimum? Okay, so we're talking about the number of people or the amount of people in line. We already considered an equation for the amount of people in line, and we want to find its minimum value. And then, so we want to find the time when the minimum occurs. Then we want to find, to the nearest whole number, find the number of people in line at that time. Justify your answer. Okay, so to find an absolute min or an absolute max, we must consider, we need to test the endpoints and we need to test the critical points. That's the most important thing that we need to know here. That's from the extreme value theorem. Absolute maxes and absolute mins must occur at endpoints or critical points. But we already know the endpoints. So what we have to do, whenever we're finding an absolute max or min, we want to make a little table.
t values and a of t values. So we need the beginning point of 0 and the ending point of 300. And we want to know how many people are in line at those times. Well, those are two values that we already know. Times 0 is our initial condition, that's 20. Times 300, we calculated in part B to get 80. But I also need to consider critical points. I'm just going to copy down that function I wrote earlier. The amount of people in line is the initial condition plus the integral of the rate in minus the integral of the rate out. Okay. That's my amount equation. And again, I need to find the critical points of the amount. And a critical point is when the derivative equals 0. So what we're going to have to do here is do the derivative of a of t. Now this looks like it's hard, but it's really easy. When we do a prime of t, 20 is a constant, so its derivative is 0. The derivative of an integral of something is just that value, as long as this is just a regular t. So the derivative of the integral of 0 to t of r of t dt is simply r of t. And the derivative over here will just be 0.7. So critical points are when the derivative equals 0. So there's my derivative. I'm going to go ahead and set this thing equal to 0. Okay, this is going to equal 0 whenever r of t equals positive 0.7, right? I'm just going to add 0.7 over. Now again, this is my rate in. This is my rate out. I want to know when the rate in and the rate out equal each other. So I'm just going to go to my graph. This will be easier to see through the graph. I'm going to go back to my nice graph. And the rate in and the rate out equal each other right here and right here. I need to find those time values and then plug those into my a of t equation. So this is a lot of work. Because it's a lot of work, you get a lot of points for it. So I'm going to do second calc intersect. And I like to go from left to right, so I'm going to arrow over here and find this first intersection. I just have to be closer to that intersection than the other one. So there's curve 1, there's curve 2. And my answer is 33.013298. So what I want to do is I want to write down all of those decimals. Because I know I'm plugging this number into my a of t function, I want to be more accurate than 3 decimal places. So right now I'm just writing that number on a piece of paper so I can write it on the screen in 1 second here. So right away, I'll go to my, and I'm going to write these two rates equal each other at t equals 33.013298. The first thing I want to do then is store this as a letter in my calculator and write that letter on here. I'm going to store it as the letter B. Okay? To do that on your calculator, here's what you do. Right now this is stored as my answer. So I just have to quit out of the screen and hit store. And I chose the letter B. You can choose whatever the heck letter you want. Just keep track and make sure it's written in the scoring region. Okay, now I need to find that other intersection. So I'm going to just crawl this thing over. Okay, enter, enter, enter. Again, I'm going to write down all of these decimals. 166.57472. They're picky about this on the exam, so we want to make sure we do this right. So again, I'm going to quit and store that. I'm going to choose letter C. So let's store that as letter C. I'm not using A because I already called my function A, but if you differentiate between a capital A and a lowercase a, that's okay too.
Okay, so now I just need to make sure that I write that in my scoring section. Okay, and now all I have to do is test B and C to figure out which one is the minimum value. I'm going after the absolute min here. So now I'm just going to go back to this equation, my amount of people in line equation, and I'm going to do the integral from 0 to B and the integral from 0 to C. Now, instead of retyping this whole thing out, a little shortcut that can save you some time, I already did this whole integral up here. So I'm just going to go ahead and grab this. And now I'm just going to change the 300 to B. I'll do B first. And I have to do that back here. If you want to retype it all out, that's fine. And I don't want it to say boo. I got to get rid of the 0 there and the 0 there. And I get 3.803. This number I can round to 3 decimal places because it's my final answer. 3.803. That looks like a good candidate for our absolute min. But we should check the other critical point too. So let's go ahead and do that. And again, instead of retyping the whole thing, I just want to change this to the letter C. And change this to the letter C. Make sure you change both if you're going to do it this way. And I get 158.070. Okay. I've done all the work. Now I just have to formulate my answer along with my justification. By the way, your justification is what you're testing, right? We tested all the endpoints and the critical points. We see that this right here, this point right here, is our absolute min. Okay? But what did they want? Did they want the time or the amount? Well, when we go back and look, it says at what time t is the number of people in the line at a minimum. So we want the time. But we also want the amount, because it says to the nearest whole number, find the number of people in the line at this time. So they actually want both. Okay? So the time was B. Now I can write this as to the third decimal. So I'd say t equals 33.013 is the time. When there are a minimum number of, there's the minimum number of people in line. Okay, that's the time. And now I have to the nearest whole number, right, because we can't have fractions of people. To the nearest whole number, how many people was that? Well, this rounded to the nearest whole number would be 4. There were 4 people in line. In line at this time. Okay, and we're done with problem 19. It's a big one. It's a doozy. It's worth a lot of points on the AP exam, and it's one that I want everyone to know really well. There was a question on problem 13. Just make sure you use your calculator on problem 13. It's that one. I should have put that you need to use your calculator there, but that's what you need to do. Initial condition plus. Talk to you guys later. Study hard. 2 chains. Bye.